Okay, so we've discussed the overall properties of transactions, and in particular the acid properties, and especially atomicity. So a transaction starts and if it completes, all of its actions are preserved in the database. If the transaction fails, anything that might have occurred while the transaction was executing will vanish. All right, well, we want to talk about what happens when transactions execute, and that's what transaction schedules are. So they're not saying do this in this order and then at this time do this and then at this time do this. What they're actually talking about is what operations occur at any point in time. And to some extent, that's a little bit arbitrary. If we've got two transactions running, one transaction might get a go for a while, it might do some operations, then it'll be swapped out and another transaction will start. And that'll run for a while, it'll be swapped out, and then the original transaction will start again. So we want to be able to talk about what happens. Oh, and the other thing I should have said too then is that the operations that occur may be interleaved. Now, one thing is that we're not interested in operations that happen inside memory. So basically what happens with a database is the database has to fetch objects, the DBMS has to fetch objects from the database, then perform operations on them in memory, and then write out the modified object, for example. So really, the interesting operations are read and write, not the stuff that happens in memory. The other operations, of course, that we've talked about with transactions are that you can start a transaction and not a transaction. You can commit a transaction and that will permanently make the effects of that transaction, or you can abort and it will unwind all of the effects. So, as I said, all the other operations are ignored. So the interesting things and the place where interference might occur are the order that things are read and written. Okay, so how does this relate to SQL? Well, a select statement obviously produces a read operation or read operations. An insert produces write operations. An update and delete produce both read and write. You've got to find the object and then change it, either get rid of it or make changes to it and write it back out again. The other thing that we're assuming here is that each of these read and write operations involves a single database item, which potentially is a single tuple. All right, well, when we're trying to talk about these things, we want to use fairly abstract and concise notation. So objects that we're fetching from the database and manipulating, we'll just call them things like X and Y. And the operations will be denoted by single letters as well: read, write, commit, abort. All right, so we'll see notation that looks like this, and this will say that the object X is read, the object Y is read, the object X is written, the object Y is written. Now, a couple of things to note. If we've got items that have the same name in two different transactions, so both transactions mention X, then we assume that we're talking about the same object. So this X object is fetched from the database into one transaction and we do stuff with it. And then in the other transaction, the object X might also be fetched and we do things to it. So the order that we do those things and the order that we write things out is important if we're dealing with a shared data item. The other thing that we don't usually mention begin, we just assume begin happens and then the first read or write operation occurs. So we kind of count the start of a transaction as the first operation that occurs. And similarly for commit or abort, we don't tend to write them explicitly unless we're actually talking about the effect of the commit or the abort. Okay, so here's an example of how we might treat SQL and write it as a schedule. So the bank transfer example, get the balance from the source account, that's a select statement which reads in a value. Get balance from destination account, another select operation that reads in a value. We do some checking, this happens in memory, so we're not interested in what happens with it, but we are interested in what happens when the values are changed. So here we're updating the source account by subtracting, and here we're updating the destination account by adding. So if you want to abstract those a little bit, X is the source account, Y is the destination account, and the whole transaction, assuming that we have sufficient funds, is going to consist of those four operations. Now notice that I said on a couple of slides ago that an update involved read and write. Here I've only written the W part of that, and kind of the assumption is that, sure, an update is a read followed by a write, a read followed by changing the tuple and then writing it back out again. We assume that an update itself is an atomic operation. So overall what we observe is simply the write component. That's the important component as far as concurrency is concerned. Okay, so if we've got multiple transactions that run in parallel, well, each transaction certainly, if you look at the order of operations that it does, it's always going to be the same. Read X, write X, read Y, write Y. If the same transaction happens to run concurrently, well, we might observe something like this, but the first example is when there's no concurrency. So this first transaction runs, does all of its read-write operations and finishes, and then the second transaction runs. If they run really in parallel, then the operations are going to be interleaved. So we might do T1 does a read of X, T2 does then T2 does a read of X, then T1 does a write of X, then T2 does a write of X. Now remember that when we do a read, we copy the data objects into the transaction's local memory, where we may make changes to it. So here, both of these transactions are reading the same tuple, and they're both making changes to that tuple. So some of these orders of operation don't cause any problem at all. If you've got no concurrency, then the transaction runs, it finishes, then the same, or conceptually the same transaction runs again and it finishes, and we get our results. And if the two operations happens in the other order, we might get the same results as well. Now what's important about sequential execution is that we start in a consistent state. I talked about what consistency meant in the transactions video. So basically it's the state of the database that satisfies all of the constraints. We execute the transaction, that puts us into a new state of the database, but that state is also consistent, satisfies all the constraints. This is assuming that T1 is a valid transaction, so it's actually doing the right thing and updating the database appropriately. Alright, so we've ended up in a consistent state, then we run T2, we end up in a new consistent state, we run T3, and we end up in a new state which is also consistent. But as soon as we start running these transactions in parallel and interleaving the operations, we can end up with problems. So let's say T1 and T2, we know they're both consistency preserving transactions, different transactions for the sake of argument. If we run them sequentially, we end up with a valid state. If we run them in parallel, T1 running at the same time as T2, then it's possible that we can end up in a state which is not consistent. So somehow the interplay of the read and write operations in the two transactions, the order that those operations happen to be done, has caused the overall effect of the two transactions to not be like this, but to produce some weird hybrid incorrect state, if you like. All right, so serial schedules where we've got transactions running one after the other are fine. They're always going to produce a consistent final state. These two orders may result in a different final state, but guaranteed that if T1 and T2 are both valid transactions, then the state that we end up with at the end here is going to be consistent. Maybe different, but it will be consistent with all of the constraints. Okay. Concurrent schedules, however, can interleave the operations in arbitrary ways. Now, it turns out that this interleaving of operations happens to be harmless, and it will produce the same effect as if we'd run T1 and then we'd run T2. So that's an important notion, that this concurrent schedule produces the same effect as a serial schedule, and that property is called serializability. I'll talk about that on the next slide. Or no, we won't. We'll talk about it in the next video. However, there are orders that we can do things that will cause problems, and they're called update anomalies. And so we end up with the system in a state that doesn't make sense relative to the original state and to the effect that was supposed to be produced by the individual transactions. So some ordering of operations is bad, some ordering of operations is harmless. So what all these concurrency control schemes are all about are really making sure that the operations execute in a sensible order that's going to lead to a consistent state. All right, so let's have a look at these, an example of an update anomaly. So here we've got two concurrent transactions transferring money from the same source account into the same destination account. Happens maybe there are two different people who own the account, so it's a shared account. They're both doing transfers at different branches because, you know, they happen to work at different places. They go off in their lunchtime and they make this transfer. All right, so the initial values of the two accounts, the initial balances, the X account has 500, the Y account has 100. If we executed T1, then we executed T2, this is the state that we should end up with. So $300 should come out of X, and $300 should go into Y. So subtract 300, we get 200, add 300, we get 400. Right, let's see what actually happens. So X reads, all right, so now we've got to talk about these columns. This is the value of X in T1's local memory. This is the value of X in T2's local memory. This is the value of X as stored on the disk. Okay, so T1 reads X, so we copy 500 into T1's local memory into an object called X. We then subtract 200, it now has a value of 300. Then we read X again. In the database, X still has the value 500, so that's the value that's copied into X in T2. Then T1 comes along and writes out its value of X, which goes to the database. All right, then T2 does some work. It subtracts the value 100 from its local X and writes the value of X to the database. So Subtracting 100 gives you 400 because the value it read in was 500. We take the 400 and we write that to the database. Oops. So the effect of T1 has been lost. So it was supposed to reduce the value of the X transaction by 100, by 200, sorry, which it did, and then wrote that out. But then T2 came along and overwrote that value with its version of a modified X. Okay, so that's a problem. That two decrements on X and decrements of 100 and 200 have resulted in an overall decrement of X in 100. Doesn't make, of 100. Doesn't make sense. Right, so let's have a look at Y. T2 then reads Y straight away, cracking on with work. So 100 is the value that was in the database at the start. Then T1 reads in Y, also gets 100. T1 adds 200 to Y and then writes it out. So it writes 300 to the database. And then T2 takes the Y value that read in before, adds 100 to it, and then writes that value to the database. Once again, the same kind of problem as we had before. The effect of T1 that we produced here has been overwritten by the effect of T2. So rather than having X with a value of 200 and Y having a value of 400, we've ended up with X in the database having 400 and Y having 200. Now, I guess the bank wouldn't complain about that because the amount of money in the system has been preserved, but the owner of the X account will be laughing because they transferred $300 out and the overall effect was as if they'd only transferred $100 out. And the owner of the Y account will be angry because they were told that they were having $300 added to their account, but they've only had $100 added. So this is an example of the order that things are done here and the interplay between the local copies of an object and the value stored in the database can result in the overall effect of concurrent transactions being, well, leading to an inconsistent state. Right, so how to fix problems like that? Well, you've got to make sure that these operations are run in an appropriate order. That's all to do with concurrency control, which we're not going to look at in this course. But one thing that we will be looking at is, all right, we've had a transaction has run. Has that resulted in a sensible order, a sensible outcome, or has it ended up with some kind of update anomaly? And that's the topic of the next video.